In our ongoing exploration of the cosmos, there is a fundamental physical phenomenon that has always captivated our attention: gravity. But what exactly is it? In elementary school textbooks, we often see a familiar image of an apple falling from a tree, a simple occurrence that hides profound physical laws. Today, let's boldly dive into the mechanisms behind this phenomenon and reacquaint ourselves with its nature. First, let's look at how Sir Isaac Newton drew inspiration from a falling apple to eventually derive the universal law of gravitation. The story of gravity is a long one, so consider this an invitation to a deep journey of understanding, but before we dive in, please remember to like, share, and follow. Our understanding of gravity as an attractive force is largely credited to Sir Isaac Newton in the 17th century. According to legend, Newton observed an apple falling in an orchard and noticed it always fell perpendicularly to the ground, as if acted upon by some force. This led him to propose the law of universal gravitation. So, what does this law describe? An ordinary apple increases its speed as it falls. Like all objects on Earth, the apple has mass, but its mass is negligible compared to the Earth's. According to Newtonian theory, the gravitational force between the Earth and the apple depends directly on the product of their masses and is inversely proportional to the square of the distance between them. Simply put, any objects with mass and energy, like the apple and the Earth, attract one another, and they exist in a state of free fall relative to the more massive body. This relationship is defined by a famous formula, stating that gravitational force equals the product of the primary and secondary masses divided by the square of the orbital radius. Newton modeled gravity as a field surrounding all matter, a conceptual framework still used today to explain gravitational interactions. According to the laws of motion, the Earth should also move toward the apple because the Earth exists within the apple's gravitational field, but this movement is so infinitesimal that it remains imperceptible. This is explained by Newton's second law, where force equals mass times acceleration. Even with the same force applied, objects of vastly different masses achieve vastly different accelerations. However, Newton's theory was not without its limits. He proposed that gravity also governs celestial bodies, including the Moon. The Moon does not crash into the Earth not only because of its continuous and rapid orbital motion but also due to the gravitational interaction between them, which becomes relatively smaller as the distance between massive objects increases. Newton used a thought experiment involving a cannon on a mountain to explain planetary orbits. If you fire a cannonball horizontally, it falls to the ground after a short distance. But if you fire it with immense force, say, at 17,000 miles per hour, the cannonball would remain in a state of constant free fall, never hitting the ground. According to Newton, the Moon and all other planets follow this principle. He concluded that gravity is a universal force acting identically throughout the cosmos. His laws did not contradict other findings, rather, they complemented them, such as the three laws of planetary motion proposed by Johannes Kepler. The law of universal gravitation can actually be derived from Kepler's laws. Kepler's first two laws state that planetary orbits are ellipses, meaning the distance between a planet and its star constantly changes, yet the planet sweeps out equal areas in equal times. Newton's laws described the acceleration of these massive bodies relative to their distance from a star. Specifically, Kepler's third law explains how orbital radius affects a planet's period of revolution, which is perfectly consistent with Newton's inverse square law. Despite its success, Newton's theory could not explain certain critical observations. For instance, while it modeled most planetary motion beautifully, there was one exception: Mercury. Mercury's orbit is a strange ellipse, and more peculiarly, its closest point to the Sun, the perihelion, shifts position over time in a process called precession. While this happens to all planets, the effect on Mercury was most pronounced and puzzling. Observations from Earth showed a precession of 5,600 arcseconds per century, but calculations based on Newton's theory fell short by 43 arcseconds. This missing gap could not be explained until the arrival of Albert Einstein's general theory of relativity, nearly 300 years after Newton's breakthroughs. Einstein first introduced special relativity, where space and time are treated as a single, inseparable phenomenon called spacetime. According to general relativity, massive objects warp this four-dimensional fabric, and this curvature is what we perceive as gravity. While Newton focused on the falling apple, Einstein imagined a person in a falling elevator. In free fall, the person feels weightless because they and the elevator accelerate at the same rate. Conversely, if the elevator accelerates upward, the person feels a force pushing against their feet. Einstein's equivalence principle states that one cannot distinguish between acceleration and a gravitational field from within a closed frame of reference. In Einstein's view, we fall not because of an invisible pulling force, but because there is no upward force supporting us. Unless we are being pushed by a surface like a floor, we are in a state of inertial motion or free fall. Einstein concluded that gravity and acceleration are essentially the same thing. Gravity is the geometry of four-dimensional space-time, not a force acting through space. We can visualize this by imagining space as a fabric where massive objects like the Sun create dips or curves. A more accurate model describes space-time as a three-dimensional grid of geodesics, the shortest paths between points. Planets in free fall simply follow these curved paths. As the physicist John Wheeler famously put it, space-time tells matter how to move, matter tells space-time how to curve. We cannot see the curvature directly, but we see its effects. For example, astronauts on the International Space Station move in a circle around Earth because space-time is curved, even though they feel they are traveling in a straight line. We see similar geometry on Earth. Two people walking due north from different points on the equator will eventually meet at the North Pole. No force pulls them together, they are simply following the curved lines of a sphere. This applies to light as well. Newton believed light might bend under gravity, but modern science knows photons have no mass. Einstein explained that light follows the same curved geodesics in space-time. His calculations predicted that light would bend twice as much as Newtonian theory suggested. This was confirmed in 1919 by Sir Arthur Eddington during a solar eclipse, proving that light from distant stars was indeed deflected by 1.75 arcseconds as it passed the Sun. Furthermore, general relativity perfectly accounted for the 43 arcsecond discrepancy in Mercury's orbit. Another piece of evidence for space-time curvature is gravitational redshift. As light travels away from a massive object, its waves are stretched, losing energy and shifting toward the red end of the spectrum, a phenomenon Newton's theory could not predict. In 2016, Professor Andrea Ghez observed the star S02 near the supermassive black hole Sagittarius A star. The light from the star shifted to red exactly as Einstein predicted, further validating his theory. However, Newton's model remains a competitor in certain contexts. In the 1930s, Jan Oort and Fritz Zwicky noticed that stars at the edges of galaxies rotated much faster than expected. To explain this without discarding gravity laws, they proposed dark matter. Current estimates suggest the universe is roughly 70% dark energy, 27% dark matter, and only 5% ordinary matter. While dark matter remains a dominant hypothesis, some physicists like Mordechai Milgram proposed modified Newtonian dynamics, or MOND. This theory suggests that at extremely low accelerations, the inverse square law changes, potentially explaining galactic rotation without needing dark matter. However, Mond struggles to explain the mass deficit in galaxy clusters. Ultimately, the greatest challenge for Einstein's gravity is its incompatibility with quantum mechanics. General relativity is deterministic and based on causality, while quantum physics is based on probability. At the quantum level, general relativity fails, and at the macroscopic level, quantum effects like superposition do not apply to large objects. Resolving this requires a new theory of quantum gravity. Until then, Einstein's model remains our most tested foundation, leading us to the startling conclusion that gravity is not a force, but the very shape of the universe. The speed of light is one of the most fascinating and mysterious concepts in physics, often considered the ultimate speed limit. But what if I told you that reaching this incredible speed is theoretically possible? While it seems like science fiction, the laws of physics provide a unique perspective. In this journey, we will explore the world of light speed and how we might approach this limit. First, let's look at the relationship between speed, mass, and energy. In physics, as an object moves faster, its kinetic energy increases, and its relativistic mass increases as well. The faster a spacecraft travels, the more energy it consumes and the more impact force it carries. This applies to objects with mass, but what about massless particles like photons? Light behaves as both an electromagnetic wave and a stream of massless particles called quanta or photons. In a vacuum, light travels at approximately 186,000 miles per second. Einstein's work showed that light speed is constant regardless of the observer's motion. This is because space and time are unified into a single fabric. Using the Minkowski model, we can visualize this as a coordinate system with space and time axes. If you are sitting still, you are moving only through the time dimension. If you move through space, your motion is shared between space and time. This is why time dilation occurs, a fact proven in 1971 when atomic clocks on airplanes ran slower than those on the ground. Light, however, moves only through space and does not experience time at all. To a photon, time is stationary. Because photons are massless, they are the only things that can travel at this constant speed. For humans or spacecraft with mass, reaching the speed of light would require infinite energy. Yet, in a sense, we are already moving at the speed of light through the combined four dimensions of space-time. The faster we move through space, the slower we move through time. While we haven't reached the speed of light with large objects, scientists use particle accelerators to push subatomic particles to 99.99% of that speed. We have also observed superluminal motion in the jets of distant galaxies like M87, though this is often an optical illusion caused by high-speed particles traveling toward us. However, real faster-than-light phenomena can occur in specific media. While nothing exceeds the speed of light in a vacuum, particles can move faster than light does in water or glass, creating a blue glow known as Cherenkov radiation. There is even a hypothetical particle called a tachyon, first proposed in 1962, which would always travel faster than light and possess an imaginary rest mass. While tachyons do not technically violate relativity, their existence has never been proven. For now, light remains the ultimate speed limit of our universe. As we continue to gaze at the stars, we remain curious, waiting for the next discovery that might rewrite the laws of speed and gravity. Thank you for joining me on this exploration. May you have wonderful dreams, and I will see you in the next episode.